Now we want to take a look at doing u-substitution integration with definite integrals. We've seen how to handle it with indefinite integrals with composed functions by using the inside function as u. When there was no obvious composition of functions, it was generally in fraction form, and then it was generally the denominator that became u. The question now is, what are we going to do, and how are we going to handle an definite integral with u-substitution? We have limits of integration. And remember that the definite integral says that we have to plug the limits of integration into the antiderivative function and subtract them. So the integral from a to b of f of x dx is equal to the antiderivative function uppercase f at the upper limit minus the antiderivative function f uppercase evaluated at the lower limit. So we're going to have to find the antiderivative function just as we've been doing so far, but then we're going to have to substitute in the limits of integration. But we have a problem here because when we switch to u, the antiderivative function is written in terms of u, but the limits of integration are not u values. They're the original variable values. In this case, they would be x values. So we actually have two options for dealing with this. One is to get the antiderivative function in terms of u, then go back to the original variable, whatever it happens to be, in this case, x, and then after you've returned it to x, then substitute the limits of integration since they would also be x values. That is one option. This is the option that students have a strong preference for, and I will admit that I also have had a very strong preference for it throughout my life doing calculus. However, studies show, and the statistics will bear it out, that the second method is faster, cleaner, and less prone to error. So I don't know why we all have this strong preference for method one when method two is better. So what method two does is method two says, okay, I'm going to find the antiderivative function in terms of u, which I have to do anyway. That has to happen. But I'm not going to go back to the original variable, which in this case is x. I'm not going to go back to x. I'm going to stay in u. What I'm going to do instead is I'm going to change the limits of integration from being x values to being u values. Then I never have to go back to the original variable. I can stay in u and I can just plug them in directly. All right. So what it does instead is it goes from having something that is x equal a and x equal b of f of x dx. And then it goes to f, well, let me write it a different way. Then it goes to u equals c to u equal d of f of u du. And then when we plug them in, we have some antiderivative function, and we're plugging in d minus c, where g and f are essentially the same function, but with different variables in it. F would be the antiderivative function with x as the variable. G is the same antiderivative function, but with u as the variable. So now let's take a look at what it looks like. The second method is faster, cleaner, takes less work, less prone to error. I'm going to show you both methods. I'm going to push you towards method two because statistically it is the better method. But if you still have this overwhelming preference for method one, it is perfectly valid, and I will take that as well. Okay, so let's take a look at the method side by side. So we're going to work through example 10 with both methods on either side. So we have the integral from 0 to 2 of 2x divided by the quantity x squared plus 1 quantity squared. Now, when we write this, this is x equal to 0 and x equal to 2. It's understood that those are x values because the differential is dx. That's one of the reasons that writing the differential is so important. The differential tells you what the variable is, what to expect as the variable in the integrand, and what the values of the limits of integration are. They're x values. Now we have a couple of choices for u here, but we have one really strong choice. What's our strong choice for u?
X squared plus 1.
X squared plus 1. It's a double whammy because it's in the denominator, so that's a plus, and it's the base of something being raised to the power 2. So that makes it twice as likely that that's the correct choice for u. So we are going to choose u to be x squared plus 1. Then we take the derivative of both sides and we abuse the notation and swing the dx around. Now we have been writing it every time as du dx equal to 2x, and then abusing the notation and writing du equals 2x dx. How many of you think that you could skip this middle step and go directly from the definition of u to abusing the notation and swinging the dx around? Yeah, Michael says, yeah, I can do that. All right. If you can do that without messing anything up, more power to you, do that. All right. If you cannot do it without messing something up, then don't do it. All right. So this is a know thyself. If you know you can manage to skip this step without messing up the differential, then you can go straight to the abuse of notation over here. So now we have du equals 2x dx. If you solve for dx, you get du divided by 2x, which I'll write over here so it shows up a little bit better. Now, we're going to go through method 1, which is the one that most students have this just overwhelming preference for. I can't tell you how strong it is. It's like, it's more than 80% of students want to do it this way. So we're going to look at method 1. Method 1 says we're not going to replace the limits of integration. We're going to leave the limits of integration as x values. But after we substitute for u, the differential is no longer dx, the differential is du. You have to indicate that the limits of integration are in fact x values. So you're going to write on the limits of integration x equals. It's no longer optional, it's mandatory because the differential has changed to du. If you don't put x equal, you'll make the mistake of thinking they're u values and they're not, they're x values. Once we switched back to the original variable x in the antiderivative, then you can drop the x equal since we'll be back to x. All right, so here's what it looks like. So we replace in the original integral, we're replacing the x squared plus 1 with u. So we get u squared in the denominator. And we replace the 2x dx with du. The differential has changed from dx to du. So because I'm not going to change the limits of integration, because I'm going to keep them 0 to 2, but they're not u values, I have to write x equals 0, x equal 2. That way you know that they do not match the differential. All right. Now, once I have this, it's just like one of the problems that we did earlier where Trevor pointed out that all we need to do to apply the power rule is move this to the numerator. Juan, do you have a question?
Yeah, so where I get everything besides where the 2x of the numerator went. Like
The 2x of the numerator is part
canceled?
of du. No, it's du right here. Du is equal to 2x dx. So they took the 2x dx and replaced it. Or you
Yeah,
can do,
okay.
do you see it?
Like, yeah, you skipped a step basically, because
Yep.
yeah,
I
okay.
did. I did skip
Yeah.
a step. That
Yeah,
part
there-
right there is du.
Yeah, correct.
Okay. So now that we have that, the next thing we need to do is we need to take this expression here and we need to move the u squared to the numerator so that we can integrate it. That leads us to this line that you see right here. Note that I'm still writing x equals 0 and I'm still writing x equal 2 because the differential is still du and these values are x values, so they don't match the differential du. Now I apply the power rule, and the power rule is going to give me u to the -1 over -1 by adding 1 to -2 and then dividing by the new power. And I have to evaluate between x equals 0 and x equal 2. Now, just like in the previous problem, I don't like substituting in this form. So I switch it to -1 over u between x equals 0 and x equal 2. Notice that I'm still writing x equal because I have u. And let me blow this up a little bit so it's a little bit easier to read. Okay, is that a little better, a little easier to read? So then I'm going to take this, I've got this negative here. So I applied the integration rule that says if you have a negative, what can you do with the limits of integration to get rid of the negative? Switch the limits of integration. So instead of going from x equals 0 to x equal 2, now I'm going from x equal 2 to x equals 0. All right. Now, in order to substitute these values in, these values, because they're x values, can only replace x. They cannot replace u. So I've got to go back to the original expression for u, which was x squared plus 1. So I replaced the u with x squared plus 1. And now I can drop writing x equals because these are x values and this is in terms of x. So if the values of the limits of integration don't match the variable or the differential, you have to write what they are. All right. Now I substitute in the upper limit of integration, which is 0 after I switch the order. And then I substitute in the lower limit of integration, which is 2 after I switch the order. And I subtract those two values. After doing a little bit of arithmetic, you'll end up with 4/5. And I want to pause and give you time to write down and ponder, think a little bit. This was kind of long and complicated. The real change for us came at this step right here. From what we did in the beginning, from the 1 over x squared plus 1 between 2 and 0, that's where the real difference starts from the indefinite integral to the definite integral, because now we have to plug in the limits of integration. All right. The rest of it is ultimately just basically finding the antiderivative function and switching back to the original variable. Now let's take a look at method 2. Method 2 is shorter. You can tell it's shorter. It's not shorter by a lot, but it is shorter. And part of what I like about it is it generally makes the arithmetic part of it simpler. All right, you can see in here we've got some fractions we're subtracting. The method 2 can often make that arithmetic part of the problem simpler. And simpler is good because it leads to fewer mistakes. So let's scroll back up to our original problem, which is, my limits of integration. Okay. That's not the beginning. I was like, wait a minute, what happened? Okay, so we're back to the beginning again. We're starting all over as if this is a brand new problem, but we're going to use method 2 this time, which is the method I hope that you will adopt because it's better. I am actually trying, after decades of preferring method 1, I'm trying to train myself to go with method 2. It's going okay so far. I have to consciously do it. So we're starting with the integral from x equals 0 to x equal 2 of 2x over x squared plus 1 quantity squared dx. We choose u to be x squared plus 1. We compute du, which is 2x dx, or you can solve for dx, du over 2x, whichever way you prefer to do it. 2x dx is a part of the numerator, so we can immediately substitute du in place of this 2x dx, and then we substitute u in place of the x squared plus 1. However, in method 2 says I'm never going back to x. Once I leave x, x is gone forever. I'm going to u and u only. So it also wants to find something to replace the limits of integration with. So far, out of this problem, we know that we can replace the 2x dx with du, and we can replace the x squared plus 1 with u. Now we need to replace and have something here and something here for the limits of integration that are in terms of u and not in terms of x. But we have a definition for u. So we're going to start here, and I'm going to rewrite the definition for u right here. This is our relating equation. That relates the u to x. So I start with the limits of integration. The limits of integration are from x equals 0 to x equal 2. So I make 2 lines. And I say when x equals 0, u equals, and then I use the relating equation to substitute the value of x to find the value of u. So u is x squared plus 1. So if x is 0, that's 0 squared plus 1, which gives me 1. So now what I've done is I've replaced the lower limit of integration to be a u value, like this, and it now is u equal 1. I wouldn't technically need to write the u equal, but I'm emphasizing for you guys that it is a u value. Then I do the same thing for the upper limit. When x equals 2, use the relating equation. U equals x squared plus 1. So if x is 2, 2 squared is 4, plus 1 gives me 5. So this now goes from u equal 1 to u equal 5, or I can write this without naming what the limits of integration are because they match the differential, which is kind of nice. I don't have to keep writing x equal, x equal, x equal. I can just drop them because they're u values, right? Are there any questions on that part? That is the crucial key difference between method 1 and method 2. Okay. After replacing the limits of integration with u values, we're ready to go ahead and find the antiderivative function. So again, we're going to take this expression and we're going to rewrite it in power form in the numerator as u to the negative 2 du. This part is identical to method 1. It's exactly the same. So once we get it in that form, which you see right here, then we can go ahead and apply the power rule by adding 1 to the negative 2 and then dividing by the new rule. So that's the power rule. And it goes between 1 and 5. And I'm going to make it even larger. If I can get it to show up. There we go. Okay, right there in the center. So I have u to the -1 over -1, which becomes -1 over u. I want to deal with the negative. Why do we want to deal with negatives? Why do I always switch the limits of integration when I have a negative coming out of the antiderivative? What's the reason for that? Does anybody know?
Easy to make mistakes.
Yes. Yes, Caleb is correct. If you leave the negative in there, then your first term is going to be negative. Then you're subtracting and your second term is negative. So you get a double negative. It just increases the number of negatives that you have in the problem. And the more negatives you have in the problem, the more likely you are to make a sign error. So it's strictly a technique to avoid careless mistakes with signs. That's the whole purpose of doing that. But again, that is one of the most common mistakes I see. So it is well worth doing. So to get rid of the negative, I switch the limits of integration from 1 to 5 to 5 to 1, and that makes it positive. Then I substitute the upper limit of integration, which is 1. So I get 1 over 1 minus, substitute the lower limit of integration, 1 over 5. And then I get a common denominator of fifths. So 5/5 minus 1/5 is 4/5. And I'm done. All right. Notice that in method 2, once we left the original integral, we never went back to x. We changed to the u form and we stayed with the u form all the way through. It can be done either way. They're both correct. I'll show you both methods. I'll probably alternate. But again, I do think method 2 is the most preferred and the best way to do it. Okay, it's not the most preferred. It's the best way to do it. It's the fastest way and less prone to error, even though the first way is preferred. I think people are just more comfortable with x. They really want that x. I don't know why, but we have a love affair with x, right? Okay, The Joy of X. That's actually a book, by the way, Stephen Strogatz, excellent author. If you have a chance to read some of his material, it's well worth it. He's written several books, all well worth your time. Okay, now let's take a look at this link to see what it is that we actually calculated. This is my function. In red, 2x over quantity x squared plus 1 quantity squared. And we were finding the integral from 0 to 2, which means we're finding the area between the curve and the x-axis from x equals 0 to x equals 2. So vertical lines at x equals 0, vertical line at x equals 2. We're finding the area of that shaded region. It's 4/5. So if it were square feet, you need 4/5 square feet of paint to paint it. All right, that's exactly what that represents. 4/5. Now 4/5 of what? Again, go from 0 to 1 on x and 0 to 1 on y. This makes 1 square unit. So it's 4/5 of one of these things here, which if you look at the blocks that are on the page, it would be 4 of the rows. It's exactly 4 of the rows. Let's see if I could take a picture of it. I think I closed my snipping tool. I always do that. I have a bad habit of closing it and then needing it. Okay, so let's look at this one. And I'm going to blow it up a little bigger so we can see it. So when you're looking at this, the amount of area that is exactly equal to that blue shaded area is this area right here. This is 4/5 square units. That's precisely the same. It doesn't look the same, but it is. Okay. Exactly the same amount of area. All right. Because there are 5 rows here up between 0 and 1 and 0 and 1, and I shaded 4 of them. Right. Let's take a look now at example 11, which is another definite integral from -1 to 0 of y equal 2 times y squared minus 3, the quantity to the 5th. This one, it's a little more clear what u should be. In this case, I would say that u would definitely be what? Let's hear from Roz or Jay. I haven't heard from Roz or Jay yet today. What's u?
2y squared minus 3.
Excellent. 2y squared minus 3. And then we can find du dx. And if you can abuse at the same time, go for it. So that's 4y. So du equals 4y dy. Now notice this does not exactly match what's in the problem. So I'm going to go ahead and solve for dy to get du over 4y. Now I know it's a definite integral, and I'm going to try to push you towards method 2. So we're going to switch the limits of integration to u form. So then we're going to write when y is equal to -1, u is equal to, come up here to your relating equation, which is right up here, and plug it in. 2 times -1 squared minus 3 would be -1. Can I get a thumbs up on that? I got some head nods. Okay. When y equals 0, u equals 2 times 0 squared minus 3, which is -3. So now my limits of integration will go from u equal -1 on the bottom to -3 on the top. Make sure that the order you put them into the new integral matches the order of the original. All right. Replacing -1 with -1 and replacing 0 with -3. If you don't, if you switch them up, what's going to happen to your answer? Is it going to be completely wrong and you have to totally start over at the beginning? What happens?
Sounds like it.
Well, what happens
I
when you
mean,
think about what happens when you switch the limits of integration? What does it do?
So you'd be missing a negative sign.
It would introduce a negative. So you'd get the right answer with the wrong sign. So you wouldn't have to completely start over. You could just write, oops, got limits of integration backwards and change the sign. Now, how would you know that? You'd probably need to graph it and look at the graph and go, wait a minute, there's more area above, that should come out to be positive. Or there's more area below, that should come out to be negative. So if you switch the limits of integration, you'll get the right value, but with the wrong sign. Okay, now we're going to have the y there, which we have nothing to replace it with. Then we replace the 2y squared minus 3 with u to the 5th power, and we replace dy with du over 4y. So the y's by themselves cancel, and I get a 1/4, which is going to come to the front, and I have the integral from -1 to -3 of u to the 5th du. Everything is in terms of u. The integrand is in terms of u, the differential is in terms of u, and these limits of integration are in terms of u. I'm never going back to y. Remember, in a definite integral, the variable is just a dummy variable. It disappears at the end anyway, because we're supposed to get a number, which represents area. So this is going to give me 1/4 times u to the 6th over 6 evaluated between -1 and -3. Remember, we're choosing the antiderivative function that has a constant of 0. You can choose any one you want, but if you choose the one where the constant is 0, you have one less term to worry about. So now the 1/4 and the 1/6 give us 1/24. And I can simply plug in and do -3 to the 6th power minus -1 to the 6th power. Right? I like to keep my constants out. That creates less arithmetic in the end for me to do, less chance for error. So -3 to the 6th, I do not know. I do not know that. I know up to the 5th, but not more than that. To the 6th, 729. I should have known that. Okay. 1/24 times 729. Make sure you do the order of operation. The exponent happens first. So -1 to the 6th is a +1 and it's being subtracted. So this is -1. So that gives us 728 divided by 24. They're both divisible at least by 4 because the last 2 digits of 728 are 28 and 28 is divisible by 4. So if you didn't know that rule, now you know that rule. So dividing by 4, I have 1, carry my 3, that's 8 and 2. And I can do a 2 again. So that gives me 91 and 3, and then I'm stuck. 91/3. That's what I got. And I haven't been checking my answers with my notes, so maybe I should do that. Yep, 91/3. Okay.
So I got confused. So in the u-substitution, we don't replace u with the what
With
we
the
said.
original, no.
No,
We
so we
never
just
go back.
okay, great. So okay.
That's why this method is faster. We don't have to go back to x. We just stay with u. Now, if you're finding an indefinite integral, you have to go back to x. If you're finding a definite integral, you definitely don't. All right. So an indefinite integral, you must return to x or y in this case. If you have a definite integral, you do not need to go back. All right. And I think I did have a graph on this one, so you can see what the graph looks like. It is actually a quite fascinating curve. If you look at this one, I really like this curve. I need to memorize this curve. This would be a great one for concavity, right? Concave up, concave down, inflection points, all that sort of stuff would be great. So we're looking at the area between -1 and 0. You can see that it is definitely above the axis, so we should expect to get a positive value, and we got 91/3, which 91/3 is about 30, which at first I looked at this and went, ooh, that's way too small. But look at the scale. This is going up to 100. So yeah, so this is probably about 30 square units. Half of this little block here would be 50, and it's a little less than that. So I think that's a reasonable answer. Okay, let's look at number 12. We have the integral from 0 to 1 of x squared cosine of pi/2 x cubed. Again, this one does have a front runner for u. Our front runner for u is the inside function of cosine, the argument to cosine pi/2 x cubed. The derivative of x cubed gives us an x squared, and we do see that we have an x squared being multiplied in the integrand. Remember that when you're looking for u and you're looking for the derivative of it, they should be multiplied or divided with the other stuff, not added or subtracted. So we've got a front runner for u. So we're going to let it be pi/2 x cubed. And now we're going to find the derivative and abuse the notation and swing it around. So this gives us 3 pi over 2 x squared dx. I'm going to go ahead and solve for dx. So I get dx equals du. Then the reciprocal of 3/2 is 2/3. So I have 2 over 3 pi x squared. So that's what's going to replace my dx. Now that replaces what's on the inside of the integrand and the differential, but I also need to replace the limits of integration. So now I'm going to replace the limits of integration, and I'm going to say when, if I can get my pen to write, x equals 0, u is equal to pi over 2 times 0 cubed, which would still be 0. So that one didn't actually change. When x is equal to 1, u is equal to pi over 2 times 1 cubed, which would be pi over 2. So I replace the limits of integration. 0 is replaced with itself. 1 is replaced with pi over 2. Right? X squared stays. Then I have cosine of u. Dx is replaced with 2 du divided by 3 pi x squared. Right? So the x squared is from the original. Cosine of the argument becomes cosine of u, replacing dx with this expression here, 2 du over 3 pi x squared. And I replace the two limits of integration. So I've gone u totally. So I'm never going back to x because I'm looking for a number answer, not an antiderivative. Now I need to cancel the x squareds and pull the constant out of the integral to the front. 2 over 3 pi is a constant. And then the integral goes from 0 to pi over 2 cosine of u du. Now cosine of u is the result of having taken the derivative of something. I took the derivative of something and got cosine. So I took the derivative of, what's the antiderivative of cosine?
Sine.
Sine. Excellent. So this gives me 2 over 3 pi, the sine of u, evaluated between 0 and pi over 2. I leave the 2 over 3 pi on the outside as a constant multiple, plug in the upper limit of integration, and then subtract what I get when I plug in the lower limit of integration. What is the sine of pi over 2? You hold up
Positive.
your finger. It's a 1, right? Sine of pi over 2. Sine is y. And so you're up there at pi over 2 at 0, 1 on the unit circle. So this goes to 1, and sine of 0 is 0. So you may want to review your basic trig values off the unit circle. You will need them off and on while you're doing integration. So this gives us 2 over 3 pi. All right. Now 2 divided by 3 pi is not very much. I'm trying to figure out about how much. It's about 2/10. It's not very much. So let's take a look at the graph and see if that matches. However, we got a positive value, so I'm expecting it above the axis mostly, but not a whole lot of area. Whoa, okay. Clearly this is a graph that goes berserk. What's it doing out here? Why is this solid red? Is it really solid red? I mean, should it really be solid red? What do you think?
I mean,
Isn't it just going back
No.
and forth really quickly?
yeah.
It's
Just
kind of,
jumps.
it's just going berserk. Does everybody, what's happening as it goes further out? Look at the width between the curves.
gets shorter and shorter and
It's
shorter
getting
and
smaller and smaller. So when it gets out here, it's not that they're overlapping. It's not solid. It's that the lines themselves are too thick to show the space between the lines, but there is still space between the lines. So it is not solid out here. There's still space between the lines, but the lines themselves are too thick to show the space. Now we're only looking at the integral between 0 and 1, which is right here. And you can see this is a very small amount of area. All right, very small amount of area. So that fits with what we found, that it was about 2/10. And again, if we take a picture of this one, I can show you what 1 square unit of area would look like. Come on, here we go. Okay, so this is from 0 to 2 on the x-axis and 0 to 2. So 1 is about here and here. So 1 square unit is this one right here, which I'll outline in yellow. That's 1 square block right there. And so the blue shaded region is about 2/10 of it, or a fifth of it, basically, which kind of fits. That seems reasonable. All right. Let's look at powers of trig functions and integration. This is actually a calculus 2 topic, but we cover it in calculus 1 as well. You will cover it again in calculus 2, so this is not going away. But this is how we deal with even powers of sine and cosine. And it is specifically sine and cosine. And it is pretty much where we break down the higher powers by using even powers of sine and cosine. So sine squared and cosine squared. And what we're using to do that are the double angle formulas that you see here. So these are the double angle formulas. So remember that sine squared is equal to 1/2 of 1 minus cosine of 2x. That's that double angle. And cosine squared is the same, except you have a plus sign in the middle. I always remember that because sine is an even or an odd function. So I associate that with a negative. And cosine is an even function with which I associate with a positive. So when it says integrate using u-Substitution, what it wants you to do first off, and I should get out of yellow, is it wants you to substitute instead in place of sine squared. So we get out of sine squared and we replace sine squared with the double angle formula, which looks like this. All right. Now we can distribute the 1/2 across both terms. Remember that u-Substitution is applied to things that are multiplied or divided, not things that are added or subtracted. And we definitely have some subtraction on the inside. So we go ahead and split up the integrand by distributing the 1/2 so that we get 1/2 minus 1/2 the cosine of 2x dx. This is a very, very common way to see a need for u-Substitution. I don't need u-Substitution for the first term. In fact, I could split this up into 2 separate integrals, the integral of 1/2 dx minus the integral of 1/2 cosine of 2x dx. And that is, in fact, the way that you want to think about it, whether you split it up physically or you simply think of it as split up. Notice that the first term does not require u-Substitution. You can just integrate directly. Since it's a constant, you're going to get the variable x. You would also get a plus c because it's an indefinite integral. The second one would also give us a plus c, and we're going to roll all the plus c's together because a constant plus a constant is still a constant. Now we're going to look at this one, and we're going to go ahead and integrate this one. The 1/2 is a factor that can be brought to the front, and then we have cosine of 2x. This is just u-substitution. We want to replace 2x with u. So we usually come over to the side. I like to do it in a different color so that I can see it separate from the actual integration problem. So u is equal to 2x. So du is equal to 2 dx, or dx is equal to du divided by 2. Now I substitute. So I have minus 1/2 the integral cosine of u times du divided by 2. Now the 1/2 that's on the inside can join the 1/2 that's on the outside. And this x plus c over here is just following along. And this becomes minus 1/4 the integral of cosine of u du. Okay. And now the next thing that we want to do is integrate cosine of u, which we've integrated it several times today. It becomes sine. So we have minus 1/4 sine of u plus another constant. Now the constants are sort of separate, but we can roll them all together into one big plus c. So we end up with x minus 1/4 sine of, return u to the original, since it's an indefinite integral, to 2x plus c. All right. We had to return to the original variable x because this one is not a definite integral. So we can't definitely stay with u. We have to go back to x. All right. Now, most students will not write the plus c on each term. They simply wait to the very last step and then they slap a plus c on the end, and that's fine.
Oh, I have a question. So wouldn't be the integral of 1/2, wouldn't it be 1/2 x?
Oh,
Why is it only
I
x?
lost my, no, you're correct. Thank you, Juan. I lost my 1/2 on the first one. There we go. Thank you. That would have been really bad. I would have had that in video forever. So yes, definitely. I forgot my 1/2. Okay. Questions on that one? All right. Let's look at approaching something else. This is a definite integral, but it also has a higher power of cosine. This is cosine squared of 8x dx from 0 to pi over 4. Because it's a definite integral, we can switch to u and never switch back. So we're going to start with our definition, and we're going to switch this integral to a double angle formula first of all. So this is going to be 1/2 1 plus the cosine of 2x, but not 2x. What are we doubling? What is our original argument?
8x, so 16x.
So 16x. Double check your formula. Up here at the top, it is 1/2 1 plus cosine of double the angle. So we've done that. And now we can split it into two integrals. The integral from 0 to pi over 4 of 1/2 dx plus the integral from 0 to pi over 4 of 1/2 cosine 16x dx. Do not be tempted to ever take the 1/2 and apply it to the 16. What is in the argument of the trig function stays in the argument of the trig function. What is not in the argument of the trig function stays out of the argument of the trig function. Now, the first integral here does not need to be converted to u form. It's just direct integration. So the first one is going to give us x with 1/2 on it, almost did it again, evaluated between 0 and pi over 4. The second one, we're going to have to do a u-substitution. So I'm going to pull the 1/2 to the front. And I have the cosine of 16x dx. I like to come to the side in a different color. U will be 16x, the inside function of cosine. Then I'm going to write du and abuse the notation by swinging the dx around. So I have 16 dx. Solve for dx, which is du divided by 16, and switch the limits of integration to u values. So this is going to give me, when x equals 0, u equals 16 times 0, which is still 0. When x equals pi over 4, u equals 16 times pi over 4, which equals 4 pi. Now I'm going to go ahead, and I will tell you that I tend to work kind of vertically. So I'll usually finish one term and then come back and tackle the other term. So I'm going to tackle this first term here. So I have 1/2 of pi over 4 minus 0, which is 1/2 of pi over 4, which is pi over 8. All right, so that part's done. And now I look at the second integral. I have a 1/2 on the outside. I'm changing my limits of integration to 0 to 4 pi, and it becomes cosine of u, and my dx is replaced by du over 16. The 16 can join the 1/2 on the outside and become 1 over 32. The integral from 0 to 4 pi, cosine of u du, which is sine of u. And then I evaluate that between 0 and 4 pi. Now you're going to see something interesting happen here. Leave the 1 over 32 outside, and you have the sine of 4 pi minus the sine of 0. What is the sine of 4 pi?
0.
It is 0. And what's the sine of 0? 0. So did this second integral actually add anything to the area? No, it did not. So our final value is pi divided by 8, which comes out to be roughly about 0.4, slightly less than 0.4, so 4/10. And I did have a link here as well, so we can take a look at that. Here is the amount of area that you've got. So it's about 4/10. Again, notice that 0 to 1 is, well, it's a little past here and then coming up to here. And we don't have all that area. It's about less than half. So again, it looks like a reasonable value. It definitely should be positive because it's above the axis. Okay, the next thing we want to do is we want to take a look at integrals that specifically involve exponentials and logarithms. And we will be doing u-substitution quite often when we're integrating with exponentials and logarithms.